Hello, and welcome to the second part of this lecture series on regression analysis. My name is Chris Curran, and I'm an assistant professor of public policy at the UMBC School of Public Policy. In this lecture series, we're talking about the basics of beginning to use regression as a method for estimating the effects or the relationships between two variables. In the first part of the lecture series, we talked about the ideal, the situation where we have exogenous variables through a randomized control trial where we can identify the effects, the causal effects of some policy or practice of interest. In this second lecture, we're going to look at one of the most basic of the non-causal or non-experimental approaches to looking at relationships between two variables, and that's ordinary least squares regression. So let's jump in. First, we want to address what exactly is regression. Well, regression with controls is one of the simplest ways to begin to try to address selection bias. So when I say selection bias, I just mean the idea of a variable being endogenous. So the example we used in the first lecture part was class size and achievement. And we noted that in the real world, class size often varies along with other variables. In other words, schools with, say, a small class size may also be likely to be schools that have better teachers or higher achieving students or other advantages that independently would make us likely to think that they would have better test scores, better achievement outcomes, regardless of the class size. So we think of these as bias, right? In other words, they bias the estimate of class size. If we just look at the difference between a large class size school and a small class size school, we don't just pick up the effect of class size, but we also pick up the effect of all of these other omitted variables. So we can imagine if we had some data on class size and achievement, that we could put it on a simple XY scatter plot as shown here. And we probably wouldn't be too surprised to see that as class size goes up, achievement goes down. Right? So we notice as we go further along the x-axis on the bottom, higher class size, the trend is for the achievement score to be lower. The problem, though, is that we're unsure at this point whether that effect is actually being driven by class size, or whether it's just that schools with large class sizes also have a lot of other things that independently might make achievement lower. So for instance, a school with large class size may be more likely to be in an urban environment, a low-income environment, environments with maybe lower quality teachers, all things that we know are correlated or related to lower achievement. So we're going to try to see if we can use regression to start parsing out the effect or the relationship between class size itself and achievement, net of some of these other variables that are causing selection bias. All right, so to think about what a regression is actually just a line of best fit. So if you go back to your middle school days, perhaps when you were using the TI-83 graphing calculators, and you remember putting in data and fitting a line of best fit, you were actually running a regression. So it turns out that regression, even though we're teaching it here in a graduate course, is not a concept that's all that difficult. It's just a line of best fit. A regression is summed up with the formula that we've all seen before, which is essentially the y equals mx plus b, the formula for a line. Now I show it here in a slightly different format, but let's talk through it and I think you'll see that it actually fits this traditional notion of a line. So we have the left-hand side variable, achievement, and it says achievement is equal to beta 0, some constant or intercept, plus beta 1, class size. So here beta 1 just represents a coefficient on the variable class size. And then finally we note that there's some error. So that error term E is just picking up the idea that for any given point it doesn't fit perfectly on the line. And we actually see that visually, right? We fit a line of best fit, but we know some points fall a little above that line, some points fall a little below it. And that's captured by the error term. All right, so all we have in a regression is a line of best fit. We're predicting achievement from, in this case, a single variable class size. Now, when we think about regressions, we can think about two types. In the most simplest case, what we just presented, we have what's called a bivariate regression. So a bivariate regression is just a regression with two variables, specifically the independent and the dependent variable. Now, it turns out that estimates from such regressions are subject to omitted variable bias in the same way that simply comparing means would be. So you notice in a bivariate regression, I haven't controlled for anything. I haven't dealt with the fact that there may be differing teacher quality, differing peer quality, different financial resources, and so forth. So in fact, bivariate regression doesn't actually do anything for me in terms of getting past some of the omitted variable bias. I still have estimates that would be just as biased as if I was comparing means. Luckily though, there's a fancier version of regression called multiple regression. In multiple regression, as its name implies, it just means that there are multiple variables in the equation. So instead of being a single right-hand side, a single predicting variable, we now have more variables, control variables. And what these control variables do is they allow us to remove at least some of the omitted variable bias. We'll come back in some future lectures and talk about some of the limitations of OLS, noting that OLS most of the time is unlikely to actually eliminate all of the omitted variable bias. But we'll see that it's a step in the right direction. It's a step to account for some of these omitted variables and the potential bias that are at play. So what does multiple regression look like? Well, essentially multiple regression is just like bivariate regression in the sense that it's a line of best fit. The only difference is that now instead of operating in a two-dimensional space, as we were in bivariate regression, we start operating in a multi-dimensional space. So essentially for every variable that gets added to the equation, we add another dimension. So you can imagine with a single extra control variable, it's kind of like having a z-axis come out of the board at you. It's going to 3 dimensions. And it would just be a line of best fit through those 3 dimensions. Now as we start adding further and further control variables, we start to get things that aren't visualizable, right? I don't know how to show you what 4D, 5D, 6D looks like, but the concept is the same. The notion is that we have these points out there that are based on all of the variables, and we're essentially fitting a line of best fit through that data. So we could write a multiple regression equation as shown here. We could predict achievement on the left-hand side from some intercept beta 0 plus beta 1 class size plus a series of control variables. So in this example, I control for grade level, expenditures, and whether the school is a private school. Of course, we probably think there's a lot of other omitted variables as well that we might want to try to control for. Now, when you run a multiple regression equation, what you're really interested in estimating are these betas. So that beta 1 sitting in front of class size, that's really the variable we're most interested in. That beta 1 comes out of your regression as a number, a coefficient. And that coefficient is interpretable as the relationship between the variable, in this case class size, and the outcome, in this case achievement, holding all of the other things in the equation constant. So let's just throw a few numbers in there and think about what they would mean and how we'd interpret them. Let's imagine that I run my regression and I find that the coefficient beta 1 on class size is negative 0.02. Well, this means that for each additional unit of class size, so for each additional student in the class, we would expect achievement to go down by 0.02 points, holding constant grade level, expenditures, private school status. So in other words, as I add students to the class, achievement gets lower. And we could be confident, or at least somewhat confident, that it's not just being driven by factors like the grade level, like expenditures, or like private school, because we've controlled for those things. So similarly, I would get coefficients on beta 2, beta 3. I show you another example here for beta 4 on private school. Now, private school is a little different because this, instead of being sort of a count variable like class size, this is actually a binary variable, a 1 or 0 for whether the school is private or not. So for a binary variable, we just interpret it as private school predicts a 0.12 point higher achievement than a public school. So we interpret it as the difference between the private school and the public school. So notice in all these cases, I'm interpreting coefficients as a 1 unit change in the right-hand side variable, predicting a beta-sized coefficient change in the left-hand side variable. In other words, as class size goes up by 1 unit or up by 1 person, I expect a coefficient size, negative 0.02, change in the left-hand side variable of achievement. All right, so this gives you a quick rundown on notion of regression. We talked about bivariate regression and multiple regression. And we saw that by adding a few extra variables, we could begin to control for things like private school status, expenditures, and so forth. In the next lecture, we'll begin to think about some of the advantages, as well as make a special emphasis on the limitations of OLS regression. So I appreciate your attention, and I look forward to having you join in the third part of this lecture series on OLS regression.